Hello, everyone. Thank you for joining us, joining our webinar this afternoon. My name is Mariana Sanchez from the marketing department at ECON. Today, we will talk about Slag conditioning with artificial intelligence for quality prediction. But first, I would like to give a short overview of us. ECON is people, passion, and performance. We develop technological solutions applied to industries in 4 main divisions: Smart Matrix, which are our data analytics and artificial intelligence solutions; Smart Factory 4.0, which are all our digital transformation solutions; Advanced Robotics, which are applications for cobots; and Industrial Automation, which are PLC programming, technology updates, HMI development, SCADA, and much more. Some of our engineers have more than 25 years of experience in the steel industry. We have 2 offices in Mexico and 1 in Colombia. We have been speakers in international forums like the ISTEC and the Digital Transformation Forum. We are Ignition certified integrators and also in Universal Robots. ECON believes in the importance of research. That is why we started our Applied Research Center in 2019. Our speaker is an active member of our research center. Richard Marquez has a PhD in automatic control and signal processing. He is modeling and optimization engineer at ECON. He has been scientific advisor for 25 years, more than 30 projects in academia and industry, and he has written more than 20 scientific papers. He's a numerical modeling enthusiast. We may have the participation of other members of our Applied Research Center during the Q&A. Feel free to share your questions in the chat at any time. They will be answered at the end of the presentation. Well, the microphone is all yours, Richard.
Thank you, Mariana. Well, welcome, everyone. I'm glad to be here. Thank you for attending. This is the second webinar of a series from Smart Metrics and ECON about some solutions, some proven solutions of the ECON approach to challenging problems in the steel industry. These solutions are based on engineering, modeling, and data-based algorithm. In this presentation, we are going to talk about Slag conditioning. Well, here we have the agenda. First, some context on definitions to set up our conversation. Then we are going to talk about what is a Slag conditioning, and then the solution of the Smart Metric solution to the problem of Slag conditioning. In this solution, we are going to talk about a little bit about inclusion engineering and some actual insight result we have obtained in the steel industry in 2 plants in Mexico. Finally, we are going to have some conclusions, and the last couple of minutes, we are going to have a Q&A section. Here, some goals, some webinar goals. We hope you will understand how to use, at the end of this webinar, how to use machine learning models to minimize the impact of uncertainty, to help your plant operator to choose the right amount of additions to produce a desired Slag chemical composition, and well, to how to use your and combine engineering principles and machine learning models or statistical models minimize cost and improve quality, a higher quality of your steel in your steel production. First, we have the context. Steel is made of additions from carbon to, here are some examples of addition: aluminum, lime, ferroalloys. Each addition has a different chemical composition. This is why each addition affects the steel properties in a different way. Well, with those additions, you obtain something you call a slag. A slag is this layer here over the molten steel in the case of the ladle furnace or the electrical furnace. Well, what is a slag? A slag is a byproduct of the steel production. It corresponds to about 90% of solid byproduct in the production of your steel. And well, according to the, sorry, just a second, to the World Steel Association, it corresponds to 400 million tons, or they are produced 400 million tons of slag annually. Well, we are going to work, each slag is different depending on the furnace it is produced. And in this presentation, I am going to talk about the ladle furnace slag. Here are some of the function of slag in the production of steel. For example, it protects a refractory from arc damage. It also retains heat and protect the molten steel from air. And maybe this is the most important function of slag. It traps inclusion and metal oxide, non-metal inclusion, and also provide the means for desulfurization. Well, with this in mind, here are some of the uses. From the uses of slag goes from construction to agriculture. In this particular case, we are going to talk about the slag used in steel production. How do you obtain your desired steel chemical composition? Well, you choose your steel composition, and then you choose your desired inclusion and your desired additions. And of course, with this, you are going to obtain your desired or your slag constitution, your slag composition, chemical composition. Due to the slag steel equilibrium, you obtain then your desired steel composition when you are producing or during ladle processing. Because of this, this is the importance of a slag in this case to produce steel. This is why you can read sometimes this aphorism: look after the slag and the metal will look after itself. We are going to look after the slag precisely in this presentation. What is the problem here? Well, let's begin with the chemical ladle furnace slag chemical composition. This is going to be the target. Later in the result we are going to present, we are going to have 56% of calcium oxide, for example. You see those values are in the range of typical values in the ladle furnace slag. So with this in mind, we are going to talk about the slag conditioning. Your operator knows what are the additions when doing tapping from the electrical furnace to the ladle furnace. With this information, your operator has to choose the final addition to obtain, and this is essential. He is going to have the steel chemical composition, the right steel chemical composition. even if the additions are in excess. In this case, we are going to think about two things. We are going to try to have the desired steel composition and also the desired slag chemical composition. To do that, to obtain the desired slag chemical composition, you have to answer this question. You have to know, or your operator has to know, what is the right amount of addition he has to make. So there are several solutions he has. He can implement. One solution is with his insights, with his knowledge about his process, about the plan and the processes he is running. But this is not enough. Sometimes he needs slag chemical composition. And for that, he has at hand a laboratory analysis. But the problem with the laboratory results is that they are usually not on time. They are not available in the present heat. So we have here a problem with time. The lab results arrive later. And another solution he can try is using calculations, using mass balances, for example. But the problem with mass balances to obtain the right desired slag chemical composition is that we don't know many things. We have a lot of uncertainty. We have maybe we have the ground assumption. We don't know exactly the composition or the proportion of the addition. We have information which is unavailable. We don't know exactly the losses, efficiencies, or recoveries, or simply you are controlling your process manually. So you have manual data or maybe the insight of your operators are implicit and they are not available as best practices. With this is here we have then the slag conditioning problem. The operator knows what is the desired slag composition, but for him, it is easier to have addition in excess to have the desired steel chemical composition. With these additions, because these additions are in excess, then in your process, the process you are running, you will obtain higher, and this is maybe the real problem. You obtain higher cost and longer execution time, maybe less efficiency, and even you can obtain inferior quality. How you can obtain a better solution, a more optimal solution? The operator doing addition in excess, they are not the right amount of addition, the optimal amount of addition. We are going to present the solution of the smart metric. Well, what is the smart metric solution to this problem? First, let's see the problems as opportunities. In this case, we have lab analysis and heat characteristics from previous heats. This means historical data. With this data, we are going to have insight about the process, to acquire knowledge of how is the process. And well, you can do that also using engineering principles, using mass balances. Well, we are going to use both in only one solution. In this case, this is a smart metric solution. In the left side, we have algorithm, we have machine learning, we have data. This is database based These are data-based algorithms that process the data to obtain knowledge. This knowledge is going to be used as a prediction for the engineering model, for the model we have from the process. This is with this. This means mass balances use prediction plus mass balances. With this, the operator is going to have the right amount of addition to make to obtain the desired chemical composition. Well, a better description of this, these two sides, left and right, data and algorithms and data and engineering model. We have here this slide. First, we start with the data from the present heat and from the previous heats. We have, for example, ladle furnace initial temperature. We have the previous additions during tapping, and for example, we have also the weight of the heat. Well, with this information and also the desired slag chemical composition, we use we use everything to have it can be seen as a model also, an algorithmic model of our process. And with this in mind, we obtain the predicted ladle furnace addition. How is this algorithm? It depends on your plant. We have seen that plants are unique. Still, melting shops are unique in some sense. And every plant is different. We have used regression algorithm. We have used also support vector machines and clustering to obtain the predicted ladle furnace additions. But this is not enough. You have to fit everything in place. To do that, you use engineering, you use mass balances. With the predicted additions and the computation, for example, we have here calcium oxide. We compute per component and the whole slag. You obtain finally, for example, you obtain the final predicted slag weight, and with this mass balances. But this is, you have to balance everything, and you use for that the optimizer. I mean, this is not the desired slag chemical composition. You compare this to the slag chemical composition, the algorithm proposed change. In this case, the predicted addition are changed here. And then you have, you run again your mass balances and you obtain another final slag chemical composition. This is the optimizer. And in a simpler form, this is simply a comparison. This is just a solver of a nonlinear equation. But we have seen also that you can change this optimizer and you can use a cost function, another cost function. For example, you know what are the cost of your additions, and you want to minimize, for example, the amount of addition you are using for a particular addition because of the price, or you are interested in minimizing energy. Well, as the algorithm, the machine learning algorithm can be changed, also the optimizer using a different cost function. This depends on the customer needs, of course. Well, the optimizer gives us the final and adjusted additions. Here I am going to present some results. For example, here you can see The operator, this is the result from the operator. Here we are comparing the performance of our smart solution versus our operator or the operator in the plant we have been working. So you can see the operator choose the additions in the operators in general choose the additions in excess. Here you can see that, but our solution is a little bit more concentrated, less dispersed than the operator solution. The operator solution can run over a large range of values, and our solution it's more concentrated. It corresponds also to optimal additions in the sense that you are using less addition, you are saving cost here. So also our algorithm, and this is our experience here, there are two things which are we have obtained from the implementation of this algorithm in the melting shop. The first one is the algorithm, and sometimes the algorithm chooses addition which has not been chosen by the operator. This is the first. And the second one, and this is very interesting, the operator also learns from the algorithm. The results of the algorithm serve to the operator to learn to be more precise when choosing the addition. Well, and now how our algorithm compares to the lab results. In this case, the red are the lab, here, the red line are the lab results, the lab analysis. And the blue line corresponds to the predicted solution, the predicted desired chemical composition, in this case of the calcium oxide and the aluminum oxide. Here you see our solution, our predicted solution is very close to the lab, and also close to the green. The green line corresponds to the desired chemical composition of the calcium oxide. Here, the desired aluminum oxide. Maybe in this plot, you see better that the algorithm learns through time. Here, these are the hits, the number of hits we have tested the algorithm. And through time, the algorithm learns from the process. This is why the solution are closer to the, for example, here, it follows the trends of the lab results. Well, here we have an actual HMI. Here, the programmed addition, which result in this by mass balances. This is not the desired slag composition. With the addition made by the algorithm, this is the green here, the green bar here. And with this addition plus the programmed addition, we obtain then a closer solution to the desired chemical composition of our slag. Well, now I am going to talk a little bit about architecture. What is important in the architecture unified data platform of ECON Tech? Well, you can pick a datum from everywhere, and this is available to the operator, to the quality assurance department. We have from lab results, historical data, measurements from tapping and the ladle processing. Well, these are all integrated. Here we have the model with the optimizer, the mass balances, and the predicted additions, but we have much more. We have root cause analysis. We have data storage, alarming, and even you can see your results of your plan and your mobile phone. all over the hardware you are using in your plant. Well, here my closing argument. With the solution we have implemented, we have cost saving by 25%. This means 43% fewer additions. We have also about 5% of energy savings, an increase in ladle furnace productivity of about 5% also, and less variability in the process variables of about 20%. I would like to say these are what we have, our experience, what we have seen in practice is that every plant is unique. These are tailor-made solutions, but you can speed up the implementation of this solution on top of the ECON Tech platform. Remember, all these solutions are implied both sides, the data-based smart computing in this case, and engineering expertise, modeling, and in this case, well, mass balance. Here are some additional features. You have offline simulation to improve, which can be used with your data to improve best practices. You have a better grasp of the slag chemical composition. Not only you have a higher steel quality, but you have also a higher quality of your slag. You also have continuous data recording. The solution is obtained in a fifth of the time, for example, compared to the time involved by the operator. And 100%, we have no manual errors in this case. Well, here, this is the end.